Hi guys, I'm here on page 65 to go over a couple model problems with you on integration techniques. If you find your packet and go to page 65, you'll see here that you've got all of the integration formulas that you need to memorize and have ready to use stored here on a single page. And if these aren't just second nature yet, I would recommend flashcards or whatever, but drilling as many of these as you can so that you're ready to rock and roll with all these things. I'm going to be going over the model problem on the bottom of page 65 to start right over here. So I'm given the derivative of a function 6x squared plus 8x and a value f of 1 equals to 11. I'm asked to find the value at f of negative 1. So just based on prior videos and things that we've been talking about lately, it looks like I'm being asked to find a new value and I'm being given an old value, and I need to try to find a way to represent that change. So let's not forget that new equals old plus change. That's an old skill, first fundamental theorem of calculus. So f of negative 1 is going to be equal to f of positive 1, in this case my old value, plus the integral from old to new of that derivative 6x squared plus 8x. So this is kind of interesting because when I lay everything out, that idea of classifying new and old leads to some tricky bounds here that are kind of upside down when I just make sure that my change has the old on the bottom and the new on the top. That's a structure that we have to make sure we maintain in all of these questions. And in this one, they're kind of upside down. So something that I would make sure I did in this question is, of course, populate f of 1, that's 11. But then in order to get these bounds back in the correct order, what I'm going to do is change the sign of my integral and switch the bounds so that now they're in the correct order. So that's something that we can always do if our bounds appear to be upside down. But now to get to the good stuff, I need to actually find the value of that definite integral. So here's where I'm going to run through some rules. Notice I'm opening a parenthesis. The antiderivative of 6x squared in slow motion, that's going to for sure have to have come from an x cubed. Sorry about that. And once I establish what the new power is, I take whatever coefficient I already had in front of my 6 and I multiply by the reciprocal of that new power, which in this case leads to a division by 3. Do the same thing over here. I establish what the power has to be. In this case, it's a 2. Then I take whatever was there and the reciprocal of that 2, and they kind of join forces before I evaluate those bounds. So I'm going to come over here. I've got 11 minus parentheses, then that simplifies down to 2x cubed plus 4x squared from negative 1 to 1. So the upper bound always goes in first. It's going to be 11 minus parentheses 2 times 1 cubed plus 4 times 1 squared minus parentheses 2 times negative 1 cubed plus 4 times negative 1 squared. And unfortunately for us here, this is just where we have to dig in and make sure we're being very, very careful on our computation. I get 11 minus parentheses 2 plus 4 minus another parentheses negative 2 plus 4. And if I'm not careful in the midst of this, I could lose a sign. So that's 11 minus 6 minus 2 over here, because negative 2 plus 4 simplifies down to a 2. In other words, 11 minus 4 for my final answer of 7. Not too bad here. Okay, and so now I'm on to the next model problem, which is most definitely going to be a little bit more rigorous. Above this model problem is a step-by-step breakdown of how to perform U substitution, and that's what I'm going to walk you through on this problem. One of the hardest things for students to understand is when to use U substitution and when not to use U substitution. So on the previous problem, I didn't need to because that was perfect integral, just ready to go with the power rule alone. But here I see a quotient inside of my integral. And unfortunately with integration, I don't have a neat, convenient rule called the quotient rule, or the product rule for that matter. So when I see products and quotients inside of an integral, U substitution tends to be a good strategy to attempt to handle these complicated situations. We've talked in the past about places that U can be found, and in this particular example, there's no radical or power or E, so a great place to look for the U is in the denominator of the function. So here's my side work that I'm going to establish. Let's let U equal the entire denominator of this quotient. That's 3 cosines of 2x plus 4. The first step highlighted in the U sub moves up above is to differentiate that U. So I'm going to use my trig shortcut over here, and I know that cosine has a derivative of sine, so negative sine, sorry. That's going to get negative 3 sine of 2x, and because of this little baby chain rule, I'll multiply by a 2. That's the derivative of the inside, and I'll put my dx on it. So then I'm supposed to isolate dx, which means dx is, let's see, du over, I'm going to go ahead and write that as negative 6 sines of 2x in the denominator. And that's well into the U sub process here, the red work that I've just established here on this problem. Because this is a definite integral over here, what I also have to remember is that those bounds of 0 and pi over 4 are coming to me in x's. And the biggest thing about U substitution is that I'm trying to translate this entire integral out of that variable of x and into the variable of U. So what I want to do next is establish if these x values are my bounds as x's, what would those become as u's? So I'm going to say if x is 0, that's my lower bound, then u is actually equal to 3 cosines of 0 plus that 4. I do a little bit of unit circle calculations. Cosine of 0 is 1. So I get a 7 out of this when I plug in an x value of 0. It looks like when my lower bound came to me as an x value of 0, what I'm going to do in a minute is replace that with a u value of 7. I'm going to do the same thing for the top. So let's see. If x is pi over 4, that means u is 3 cosines of pi over 2, because 2 pi over 4s gets me to pi over 2 plus 4. Again, with some unit circle considerations, cosine of pi over 2 is 0. 0 times 3 is 0, so all I get here is a bound of 4. All of this stuff in red and blue up at the top allows me to come back to my original integral and write the whole thing in u's. So I'm not going to put a 0 for my lower bound anymore, because over here in blue, what I established is new bounds for the integral. The 0 is equivalent to a u of 7, and the pi over 4 is equivalent to a u of 4. When I come back to my integral, I'm supposed to always only replace, let me make sure I annotate this, the u value and the differential. So sine of 2x stays anchored on top, but in the bottom of my integral, I'll replace 3 cosine of 2x plus 4 with a u. And I'll come over to my side work just right up here, and I'll replace dx with du over negative 6 sine of 2x. And the reason that's so helpful is because I can look at this integral and get rid of everything with x's. Those signs cancel. And I'm going to rewrite this as negative 1/6, the integral from 7 to 4, I'll fix that in a minute, of 1 over u du. This is great. If I kind of draw a line in the sand here, whoa, let me try that again. If I kind of draw a line in the sand here and only look below that line, ignoring everything at the top, I have a really easy integral to handle now. So I should not be nearly as intimidated by this problem anymore. That's the whole purpose of U substitution. Hold on. Okay, so, sorry. Okay, so like I said, now I have a really nice integral that I'm looking at. I'm going to flip the bounds. So I'd love this to have bounds from 4 to 7, but because I'm flipping those, I have to change the sign of the integral. So the original integral that I created was negative. I flipped the signs, so now it's positive, and I have 1 over u du. That's one of our nicest integration rules. This is 1/6 the log of u, and I want to run that from 4 to 7. So that's a memorized rule. Because the 4 and the 7 are u's, I get to just go directly in now. 1/6 the log of 7 minus 1/6 the log of 4. And that is a solid final answer. Sometimes the test uses log properties to simplify even further. So just a note, I could rewrite that as 1/6 the log of 7 over 4, because in log land, subtraction means division. So that's a cool rewrite that I can take on if I feel inclined to do so. Okay, so your pre-work, the video part is over. Don't forget to come over here, and your check for understanding today involves the 5 multiple choice questions on the next couple of pages. I'm just going to talk you through this real quick. Number 1, memorized rules. Nothing scary about that. Number 2, you can use memorized rules if you want to. That kind of looks to me, if I scroll back up, like this sign of ax plus b situation with an a of 3 and a b of 0. But you could also do a u sub if you want to with a little baby u of 3x. Really straightforward u sub on number 3, so make sure you do u sub there. And the one I wanted to point out was number 4. The only way that you're going to be successful here is if you do synthetic division. So just a heads up, don't forget to put a little 1 in that box off to the side. I can't write on this right now. Hold on, let me try to help you out here on question 4. In order to do this, I'd have to notice that I'm dividing by x minus 1. Hold on. And that means I put a little 1 in the corner. I line up my coefficients of 2, -3, 0, and 6. And I try to remember how to do that division and then do my integration. Sounds kind of tricky, but I think it'll be fun for you to try it. And then 5 is a nice u sub as well. So take care of those. We'll check them tomorrow. Good luck. I'll see you soon.